And you can see on the left hand side, it is trying to do the synthesis and for each and every module and trying to generate the RTL netlist for each and every block. So running this output products is very much important. Why? Because we need to make sure that whatever the customization parameters that we have entered for each and every IP core, with those configured parameters, whether we are able to generate an equivalent hardware. That means we are able to generate the RTL netlist or not, that we need to check. So on the screen, you can see RTL synthesis has been completed for counter, clocking wizard IP core, as well as VIO. And currently it is performing for ILA IP core. You might experience few set of warnings, but you can currently ignore those warnings if in case if you're getting any. So it won't affect our design as of now. So depending upon the complexity of the block design that you are performing, it will also take a significant amount of time to run this process. And it also depends upon the hardware configuration of your computer. So the output products were generated successfully. Now, and just to close the block design. Yeah, there are some 44 warnings. You need not worry about all these warnings, not an issue. So now what you do is just right click, select the design, right click on it, and you can see an option called create HDL wrapper. Because the ultimate goal is everything should be in HDL description. That means since we're using a Verilog language, everything should be in a .v file extension. That with that description only, we will be able to do synthesis, implementation, and then they perform the bitstream generation. But while designing, you have done it in the block level. So after that, you have generated the output products. That means you have generated the individual RTL netlist for each and every block. Now, what you RTL netlist means, it's like generating a Verilog code at the back end for each and every inbuilt IP block that you have used. Now, what is the main aim is to create a HDL wrapper. Wrapper means it is a top level module. Inside that wrapper, you will be having the Verilog instantiations for clocking wizard IP core, VIO IP core, ILA IP core, as well as your counter design. So that wrapper also will have extension called .v. So we need to generate that wrapper. So Vivado will automatically generate the wrapper for your block design. So you need not write any wrapper code. If you are designing any custom hardware architecture by using HDL description like Verilog, for each and every module, if you're writing description separately, and then when you're integrating all those modules, then you need to write yourself the wrapper code. That I will, if time permits, I will show you later how to write a wrapper code and all. But as of now, since we are doing a block design, inside the block design in Vivado, there is a provision to generate a wrapper automatically. So you can just right click on the design and click on create HDL wrapper. So you will get a dialog box like this. By default, it is selecting the let Vivado manage wrapper and auto update. So don't just leave the settings to by default and click on OK. And you try to observe the sources tab. It gets updated and a wrapper file will be generated and it will be placed on top. It is still updating. Just wait for the updation process to complete. Yeah, once it is updated, you can see the wrapper file has been created. The wrapper file name goes as follows: design underscore one underscore wrapper. So if you open this hierarchy, within the wrapper, you have a block design. And within that block design, you have the corresponding Verilog file, that is design underscore one dot v. Again, if you open that, again, you have a separate IP block for clocking wizard, for ILA IP core, for VIO IP core, and a block design for your counter. Again, if you open the counter design, you will be having at the leaf node your actual counter description Verilog file, that is my counter 6-bit.v. So if you open and if you check, this is nothing but the code that you have written for your counter design. In a similar way, if you try to expand other blocks, it is showing you a message like this is an IP file. Is it okay to show IP hierarchy? For large IPs, this may slow down the source hierarchical updates. For inbuilt IPs, depending upon the type of license you have, only you can go to certain hierarchical level. You cannot see all the files that are associated with that IP. Why? Because those files will be encrypted from the Xilinx side. So only you'll be having the control to just plug and play type. So just drop it in your design environment, make connections and use it. You'll be having the reference manuals like how to customize the IP and how to use it in your designs. So only thing that one is only accessible. If it is a user defined IP, then if you are providing any privileges accordingly, an end user can able to go deep down the hierarchy and able to extract the associated design files for that IP. As of now, that is a little bit a complicated task, so we need not dive into that topic. So I'm just my main motivation is to show like a proper hierarchy has been maintained by the Vivado. So under the wrapper, you have the block design. Under the block design, you have all the IP blocks. If it is a user defined block, under that block, you will be having the Verilog file. So this is the thing that I want to mention. Now, if you just open the wrapper, you can see, just try to go through the code. So it is also having a module and an end module, and the module name is design one underscore wrapper. So in our main block design, if you see, we have only two external inputs. That's it, clock and reset. So for that, in the port list, clock and reset has been defined. And within this wrapper, it is instantiating another module that is called as design underscore one. So if you just enlarge this hierarchy, within the wrapper, you have a block design. Under this block design, you have the actual Verilog code called design underscore one. If you just open in this code, this is actually, it opens in read only mode, so you cannot edit it. So this is generated by the Vivado automatically. The syntax is quite different from the one which we follow, but more or less this is also same. Again, it has a keyword called module. At the end, you have end module, and the module name here starts with design underscore one, and it has a port list again, clock and reset. And this is some interface information. that we can skip as of now. And there are few wire declarations. Why these wire declarations I will let you know. And at the bottom, you can see there are instantiations. So, sorry, this is the instantiation of clocking wizard IP. So if you see here in the diagram, we have a clocking wizard block. For this, equivalent Verilog code will be automatically developed this generated by the Vivado. Why? Because it is a built-in IP core, and that Verilog file for that IP core has a naming convention as follows: design underscore one underscore CLK underscore viz underscore 0, 0. This is the name, and this is the name of the module. For that module, there is also an instance name called clock underscore viz underscore 0. And in this module, you can see in the diagram, we have clock underscore in1 reset as the input, clock underscore out1 and locked as the output. So in the Verilog code, you can also see clock underscore in1, clock underscore out1, locked and reset. The arrangement of input and output is little bit interchanged, but input, output, output and input. You can put it in a, you can define the port list in any order, but always you need to make sure like for the right port, you are making the right connection or not. So for this, you can see how Vivado has connected to this clocking wizard IP core. It has connected a wire. That wire name is called clock underscore in1 underscore 0, 1. And this wire is directly connected to the clock, clock port of the actual module that you can see here. That is coming by way of an assignment. So actual top module has a clock. That clock is uh, that clock is nothing but this clock in the diagram. This clock is connected to clock underscore in1 via this wire. Okay, I'm just highlighting. See, this is the output clock. This is the clock underscore in1 of clocking wizard IP core connected via this wire. And this wire name is called clock underscore in1 underscore 0, 1. So output clock is coming to clock underscore in1 underscore 0, 1. And this one is connected to the clock underscore in1 of the VIO IP core. Similarly, so what are the interconnections? These all are nothing but wires, right? At the top level, you are interconnecting each and every port with of other modules by way of a wires, right? So all these wires, it has connected appropriately. So this is the instantiation of clocking wizard. This is the instantiation of ILA IP core. This is the instantiation of our counter design. This is the instantiation of VIO. So this all code will be generated automatically. And this you cannot open the Verilog codes of clocking wizard ILA and VIO, but you can also open our Verilog code for a counter design. So when you're generating the output products, so Verilog codes for the IP blocks will be generated at the backend. And once you create a HDL wrapper, in a wrapper will be created by instantiating all these things. So this is how the hierarchy looks like. So next, now our main aim is to implement this on the FPGA. So before implementation, yesterday I just intimated you like once the design has been completed, we have to do simulation. As of now, I'm skipping the simulation. Why? Because anyhow, to save time, anyhow, if you do simulation, it will work. Anyhow, earlier we have simulated our module, right? Yesterday also we simulated, today also we simulated and checked our module and is anyhow working fine. On with this IP arrangement also you can do simulation. Even then also you will be able to get, but at this time what you have to do is you have to capture the not the output of counter, you have to capture the output of probe in the simulation environment. So as of now that is not required, we will skip. So directly we can proceed with synthesis to convert the Verilog description into gate level or RTL netlist. After that, we will do implementation to convert the gate level netlist into FPGA netlist. After implementation, we will generate a bit stream and then program our FPGA. But before that, now we need to define in a constraints file where to connect this clock and reset inputs of our entire design on the FPGA. So for that, a constraints file is required. So before performing the synthesis and implementation tasks, it is advised to write a constraints file. So first check whether any constraints file is already available in the project directory or not. Why? Because the design sources can be any number of device design sources. You can have any number of Verilog sources in the design sources folder, but within the project, you need to maintain only one constraints file. If at all, if you are having any constraints file, then don't create any new constraints file. You just to define all your constraints in that constraints file itself. In my case, I don't have any constraints. Even in your case, if you don't have any constraints, then click on add sources and select add or create constraints. You can give any generic name. In my case, I'm giving design underscore one underscore XDC. XDC means Xilinx design constraints. Even the file extension is also .xdc. So please you don't get confused. And click OK and click on finish. So a new constraints file is generated. You can just open it. Now what you have to do is you have to define the constraints for clock and reset. So to define the constraints, yesterday I have told you, since we are dealing with basis tree, FPGA development board. So each and every FPGA development board will have a master XDC file. So for the basis tree, we need to source the basis tree master XDC file. So just to Google it, in the first link you will be getting in the GitHub. So this is the basis tree master XDC file. So in this, there is the first one is the clock constraints. So this one I will just copy and I will just paste it over here. Just maximum. Yeah. So set underscore property package pin W5. So on the FPGA development board, on pin number W5, the actual on the pin number W5 of FPGA, the actual crystal oscillator clock which is present on the board is connected, which operates at a frequency of 100 megahertz. So to this port, I want to connect the clock input terminal of our block design. So I just renamed the port to clock. And the clock is having a time period of 10 nanoseconds with a duty cycle of 50%. So 10 nanoseconds means 100 megahertz. So my clock constraints is over. Write the constraints for the research signal. So for the research signal, what I am doing is I will be configuring a push button. So let me just open the basis tree FPGA development board picture. So this is the picture, right? So here, the label number 7, you can see there are 5 push buttons available. So I'm going to configure the center push button as the reset button. So the constraints file. These are the constraints for switches, LED, 7 segment display, and here is the for the push button. So I'm just selecting the push button and I'll just paste it. And I will just connect the port. Please. So this is a physical constraints for the U18 pin. The push button C is connected to the FPGA and IO standard operating voltage, that is 3.3 volts for that push button uh, defined. So now what we have to do is we have to do run synthesis, run implementation. So you can click on run synthesis, or else you can directly click on generate bit stream. What it will do is it will directly first do synthesis, then implementation, followed by bitstream generation in a proper sequence. After that, you can just open the log and you can just maximize it, and you can just check how log is being updated. So this process will take some around 2 to 5 minutes of time. We will see once this is done. So I hope everyone are following along with me. So in the meantime, if anyone has any queries, I can just interact with them and I can resolve until this process gets completed. So if anyone has any queries, you are welcome to ask. So synthesis has been completed. How it is performing. While during synthesis and implementation and bitstream generation, there might be few warnings, so you can ignore them, not an issue. You should not have any errors. If any errors are there, it won't generate any bitstream file. Even with the warnings, so depending upon the severity of the warnings, if the severity is very much less, even then if you have warnings, the tool will perform implementation and bitstream generation. Mahesh sir, and kindly make arrangement of the basis tree boards so that we will just dump the program and we will verify its functionality.
So I have given sir, given the board distributed.
What sir? Your voice is breaking.
I have given the board.
Okay, sir.
You can continue.
Okay, okay. Sir. Yeah, kind attention participants. Actually, I'm waiting for the bitstream generation. As you can see on the screen. So synthesis is completed. It is performing implementation. I think implementation is also going to complete. After this, bitstream will be generated. Once the bitstream is generated, I will guide you with the further steps. So now the implementation is complete. It is generating the bitstream file. Yeah, now you can see the bitstream generation is also completed successfully. Uh, if you are getting this message, then we can proceed for direct implementation. So you can click on Open Hardware Manager and click OK. So it will be opening you the Hardware Manager. So once the Hardware Manager is open, you just make your FPGA connections. Just connect the JTAG cable to the FPGA and other end to your host computer. As you can see on my screen, I'm showing in front of the camera. So you can just power on it. A red LED will be glowing. Now what you do is click on the open target and click on auto connect. So the cable drivers will try to check the try to make an establish a connection with available target which is connected to the COM port. Uh, it just takes few seconds to identify the target. So on the screen you can see the target has been identified. That is Xilinx XC7835T. That is, it is properly pointing out to the basis board. Now you can click on the program device, and now you can just pay your attention. Earlier, when we have done the programming of our FPGA, we have noticed only the bitstream file. Uh, and there is also a section called debug probes file that was empty earlier. Why? Because we have not used any debug probes. But in our today's design, we have integrated a VIO IP core and ILA IP core. These two cores are specially referred to as debug IP cores. As the name suggests, debug, it is used for debugging the hardware in real time. So these cores are very much useful to check the functionality of the hardware that is sitting on the FPGA. So, and it also helpful for debugging if at all there is any errors or logical errors or anything. If you want to identify where your circuit has went wrong, why it is not generating the outputs properly. So whatever the output from your internal circuit that you want to not only output external outputs, whatever the signals that you want to monitor and check how they are performing, you can pull out those signals and directly connect it to the ILA IP core so that you can just monitor those signals. So these IP cores are called debug probes. So for these debug probes, the necessary bitstream files associated for this will be generated separately. And for the hardware, it will be generated, the bitstream file will be generated separately. So these two files will go and it will sit on the corresponding hardware will be released on FPGA. Then, since we have used this debug IP course, a two-way communication portal will be established and a new terminal windows will be popped up on your screen. Uh, Through that, we can just run our hardware with the, you can make your circuit to run. Once the circuit is generating some outputs, that outputs will be captured by the core which is sitting on the FPGA. And once the once the output has been captured, that will be redirected to your host computer via the JTAG cable. And in the host computer, you will be having a terminal. In the terminal, you will be able to visualize the data. Actually, we don't say it as a pure 100% real time. It is near to real time. So first, your circuit will work. It will generate the output. The output is captured and it is stored in some of the memory elements on the FPGA. From that, these IP core, what it will do, it will send the data serially via the JTAG cable, and that will come to your host computer. From the host computer, what again the Vivado will do, it will try to interpret the data in the form of a timing waveform and it will show. So in order to complete all this process, this process completes with a small delay. So you are not actually seeing the data in real time, but it is near to real time with a fraction of delay. So we just click on the program button. So the FPGA will be programmed successfully. Once the FPGA is programmed, you can see in front of the camera I'm showing. So this green LED will blink, indicating that the program is successful. So once the program is successful, what you can see on your screen, two windows has popped up. I am just maximizing it for your visibility. So on the first you can see HW underscore ILA underscore one, that is hardware integrated logic analyzer window, and second one is the HW underscore VIO, hardware virtual input and outputs. So actually we have added two IP cores, right? VIO IP core and ILA IP core. VIO IP core is used and it is configured to provide the enable signal to our block design, to our actual counter, and ILA IP core is configured to capture the count output of our counter. So in the VIO, you can see none of the probes are present as of now. And here you can see press the plus button to add probes. So you click on the plus button and here it is showing you one probe. Why? Because in VIO, we only configured one probe that is connected to the enable input of our counter. So you double click on it and you just add the probe. Now what you do is the probe is added. Here you got a drop down menu. You can provide the value of this probe as binary 0 or binary 1 since this probe is a single bit. By default, let us assume first we will give a binary 0. So the 0 is fed. How you know that the 0 is fed? You just minimize it and in the tickle console at the bottom, you can see this one, a blue command. So this is indication that we gave a value 0. You try to give a new value. Again, you will get a new tickle command. So whenever you're passing a data. So first we give a 0 to value. Now what you do, you go to the ILA. In the ILA, you can see by default, since we connected only one output to our ILA probe, so that one output is available here. Uh, just maximizing it just a minute. So my counter 6-bit underscore 0 count. This is a 5 down to 0. That means it is a 6-bit counter out. So by default, it is in hexadecimal. You can change the radix to unsigned decimal for ease of interpretation. Now here you can see just a play button. That play button says like run trigger for this ILA core. Now if you click on this, what it is showing, it is showing some constant value that is 33. Why? Because the counter has started earlier when you gave 1 and next we gave 0, right? So somewhere in the down the line, when you disable, at that time, the count value is 33 and the 33 is held continuously. So that's why you're only seeing 33 all the time. Now what you do is you make the value to be 1. As soon as you made it enable value as 1, the counter is in free running mode and it is continuously generating the values varying from 0 to 63. After that, again, it is becoming 0. Again, the cycle continues forever. So within a fraction of seconds, the counter is continuously counting. Now what you do is you run trigger one more time. when you run this trigger, what it will do is it will try to capture up to 124 sample values, and those values will be visualized in the form of a timing waveform. So if you run trigger, so it has captured 1024 sample values. So that's why you're seeing it in the black color. So now what you do is you just zoom it little bit. Now you can see the actual timing waveforms. So I think whether this is in radix, unsigned decimal, okay. Now you can see 17, 18, 19, 20. So like that, it is keep on going. So up to 63. So here is the 63. Again, the counting sequence has been started freshly. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on. It is going up to again 63. Once the counter is reached the maximum, again it is reset to 0. Again the sequence continues 0, 1, 2, 3, 4, 5. So since we made enable to be high continuously for all the time, this sequence is being repeated continuously. So the counter is freely running for all the time. And I told you only 1024 samples only it will capture. That is why, because this ILIP core is configured with a default depth memory depth size of 1024 samples. So as I told you earlier, along with your actual counter hardware, there is an additional hardware overhead that is being realized inside the FPGA using the FPGA resources. And what is that additional hardware realized? The additional hardware is realized for the VIO IP core and ILI IP core. But these two IP cores are not part of your counter design, but only these are additional peripheral or extra logic or extra hardware overhead. Why you are adding it? In order to verify your functionality of your actual counter in real time on FPGA. So how this ILA works is like it generally internally store consists of a memory, and you are connecting your output, that is count, to the ILA, and the count is an output wire. On that wire you are getting continuous output at each and every clock cycle when enable is active high. So the count values are coming continuously. So what this ILA is doing is it is cyclically storing that obtained value inside its memory, starting from 0 to 1023 memory locations. When the last memory location is filled, again it goes to the first memory location, and again it fills the values sequentially. So whenever you are running the trigger, the captured output, whatever it is there inside the memory, that is passed serially from the data cable to the host computer, and from this you are able to visualize the data that is being captured. And you can also set up this trigger settings. So I didn't give any settings over here. I just run the trigger randomly. So that's why you can see sometimes the starting sample value is 13, and sometimes the starting sample is 38 now. Again, if I run the trigger, the starting sample is 57, like that. So, depending on whenever you want to capture the data, you have to define some certain conditions. When enable is toggling from 0 to 1 or 1 to 0, then only you capture it. Or like that, whenever a data valid is high,
The
then only you
starting sample
capture.
value
Like
is
that, you can
13,
define some
and sometimes
conditions
the
that is
starting
called
sample
as
is
trigger
38
setup.
now. Again, if I run the
If you're
trigger, the
setting up
starting
any
sample is
trigger,
57,
then
like
at
that.
that time, what you can do is
8 now.
uh,
Again, if I run the trigger, the starting sample is
you can
57,
precisely
like that.
capture the
So,
required data, and then you can
depending
check
on
the
when you're,
functionality.
whenever you
In this case, this is a normal random
want to
nature.
capture
You are just running the trigger,
the
and
data, you
randomly
have
at
to
that instant, whatever the output is there at that time, it is captured. There is also provision for you to give conditions. When this condition is happening, then only you capture the data. Then at that time, At those conditions, you can check how the hardware is responding and how the output is generating. In order to define all those triggers, what you have to do is here in the trigger setup at the bottom, you can see here you can just add it, and you should also have some status signals. Here we have only the data signal. With this data signal, I think we cannot set up the trigger. I think it is very difficult. Okay, we will just give a try. Whenever the count value is becoming 0, then we try to establish the trigger. So like that, you can use some conditions and then you can launch the trigger. Then depending on when that condition is valid, at that time, whatever the data is there, at that time it will capture the data, it will store it in the memory. Once the memory is fully filled, then it will output the data from the read the data from the memory and output it via the JTAG cable. From the JTAG cable, it will come to your host computer. From the host computer, what it will do, it will interpret in the form of a timing waveform diagram. Then you can visualize it. So if I just run the trigger, now you can see here I kept the trigger setup and how I gave the condition is check here. See, we have an output called count. I gave an operator called if count double equal to, and double equal to what type of a value? Unsigned decimal equivalent to 0. Then I'm asking it to start the trigger at that instant, and then you give me the whatever the output it is coming, you just give and you just provide me. So in that manner, I have given this setup, trigger setup. So if I give in that way, what it is doing. So now you run the trigger continuously. It is starting from the 0th output. So we are getting it properly. Next, what you can do is I will just change this value to 23, and now I run the trigger. So whenever the value is 23, at that time it is trying to capture the output and then it is giving it. So this trigger setup is very important. Why? Because I told you earlier, right? Say for example, we have a module like this and we have some data out. And for this data out, whether it is a valid data or not a valid data, that is being indicated by a status signal called data out valid. So we will use some flag output like this. So this data out valid will come only at a particular instance. Whenever this data valid is coming, then only it indicates that whatever the data coming on this line is a valid data. And you are very much interested to capture only that data. And outside that interval, whatever the data is there, that we treat it as a junk or a garbage. So if you don't give a trigger setup like this, like whenever data valid is equal to 1, then only you capture the data. If you don't give like that, then what the trigger setup will do, it will capture whatever the data that is coming on data output. So for example, it has started capturing data from here. So from here to here, I told the data capturing will depend on the total number of configured memory depth size. So in our ILA, we configure the memory depth to be 1024. So from here to here, actually it is a garbage data or no data, maybe a 0 data or some unknown data, garbage data. So what this trigger setup, if you don't give a valid trigger setup properly, what it will do, it will capture the data in the unwanted region and it will give you, and you will not be able to observe the valid data. So whenever you are not able to observe the valid data, in this case, you are not able to observe and you cannot evaluate the functionality of you cannot check the functionality of your circuit. In that case, what you can do, you can give a trigger setup with these conditions. Then what it will do, it will only capture the data whenever data valid is coming high. So whenever data value is coming high, at that time only it will capture the data. In between, if there is a change in the data, the data will not be captured. So in this case, since the memory is very much limited on FPGA, by using this phenomena, you can capture the relevant data and check the functionality of your design. So I hope this is very much clear.
Hello.
Hello.
Good afternoon, sir.
Yeah, good afternoon, sir.
Sir, I have got smart doubts, sir. I'll share my screen, sir. I have got five thoughts, sir.
Sir, I'm getting echo. Sir, just a minute, sir. Give me some time.
Sir, just
I have closed the screen sharing from my side, and you are free to share the screen from your side. But just give me 2 minutes. I got one important call. I will
hello.
just answer and I will be back.
Speak, Anji.
Sir, just 2 minutes. I will be back again. Yeah, sorry guys. I got an important call. That's why I have went. I am back now. I have completed the demonstration from my end. If the students have any doubts, I can take it up. So someone wants to share the screen, right? Yeah, please share the screen. I will look into the issue. Hello. Hello. Hello, Mahesh, sir. Hello, no one is available.
Hello, sir.
Yes, sir. Who is this? Hello. Hello.
Srinu sir.
Mahesh, sir. Hello.
Is my voice?
Uh, no,
Is
sir.
it
Your
audible?
voice is not audible. It's breaking in between.
Hello, sir. Is it audible?
Now it is fine, sir.
Sir, some of the students have a doubt. They are unable to dump the program on the board. There is an issue with that. Can you please resolve it? They have shared
I
their
can.
screen.
Okay, sir. I can. I will try to address it. So where is the issue, sir? Can you please tell me? Why do so many number of probes are there in the ILA?
Yes, sir. It's on a doubt, sir. I have got many clocks there.
Sir, can you please open your block design once?
Yes, sir.
You can do one thing, just close the hardware manager. Now you go to left hand side, open block design. Okay, clock reset. Oh, so you can close it. Yeah, design seems to be fine. Okay. You have completed a bit scheme as well, right? Okay. Once close the block design, please. On the top right side corner, the blue color bar. Yeah. Just open the project summary. Just a minute, please hold on. This is fine. Sir, just open your sources, please. So design underscore to design is in this station. Go to this top. To find, just open the hardware manager, switch on the FPGA board. Just show the constraints file, please. Once you can click on Xilinx underscore DC. Yeah. Clock W3 waiting. Okay, fine. Just click on the program device. Design to graphic upgrade. Yes, okay. Why these many clocks are coming from there? Okay, just go to VIO on the right side. Right, 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 right. Right, sir, right side. Right side tab. No, 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 just VIO, VIO. HW interest. No, 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 don't close, don't close. Yeah, yeah, yeah. Yeah, you click on one, change the value to one. Value, yeah. Now go to ILA, adjacent block, adjacent tab. Now you just run the trigger. So one error and running. First one. As you one. Okay, I understood. You close. Click on OK, sir. Just to close the hardware manager. Turn off the FPGA board. Close the hardware manager. Generation of output products is an error, so that is a big problem. Just open the block design. Maximize it, please. Just click on the clocking wizard. Open the customization window. Clocking wizard, yeah. IP customization window. Go to output clocks. Why it is not. Sir, only you are only having the issue, or rest of, or all the students are having the same issue?
Sir, I heard that issue.
So remaining students are able.
Remaining.
So the remaining students were able to do verify it on the board.
They're in process, sir. They still didn't reach up to this, sir.
Oh, they are still doing processor. Sir, better you do one thing. Create a new project and start from scratch again.
Copy all the code separately and do it.
Yeah,
Fine, sir.
yeah.
We will do it and we'll update you.
You can just, why? Because I think same directory is being used for 3 different experiments, right? If you are that too, I think.
File, whether it will work.
Sir?
If the current .v file on the top of the module, will it work now? Okay, we will try this, and if it doesn't work, we will do it in a new project and let you know what is the result.
You can do one thing. What you can do is you regenerate the output products and regenerate the wrapper, and then perform synthesis, implementation, and bitstream. Then it should work. Otherwise, what you can do is you can just copy the counter Verilog file, create a new project, import it, and then make the necessary connections with the IP cores.
Sure. Okay.
Okay, okay. Sir.
Hello, sir. Meanwhile, can we take some time for this, or do you want to continue?
What, sir?
Can we take some time for this, or do you want to continue with the next topic?
You please take some time, sir. Why? Because this is a very important concept, and they should have a hands-on experience on this. If they are getting it, then then only it is, then only we can proceed it further.
Then we'll take some time, and after resolving these issues, I will call you back.
Yeah, sure. I will be present online. If you have any queries, I will be addressing it.
It may take some half an hour time for this. I will call you, that's fine.
Yeah, okay, no problem. You call me, sir, then I will hang it up.
Okay, sir.
Okay.
Sorry, what is sir? You are mute, right? Okay, next step ఇది సరే ఇది కంపైల్ అయింది అనుకుందాం. నెక్స్ట్ యాడ్ చేయాల్సింది
సిమ్యులేషన్స్
సిమ్యులేషన్ సోర్సెస్ ఎందుకు
అంటే
టెస్ట్ బెంచ్ అవసరం లేదు. యాడ్ ఆర్ క్రియేట్ కన్స్ట్రెయింట్స్. అడ్మిట్ హిమ్ సార్. అడ్మిటెడ్.
Yeah. Yes, sir.
Hello, sir.
Yeah, tell me, sir. Just share the screen, sir.
Sir. Screen.
Yes, sir. Yes, sir.
Do you see my screen shared?
Yes, sir. I am able to see. So what is the problem, sir?
Sir, are you able to see my screen, sir?
But here not working. No internet is.
శ్రీను, యాక్చువల్గా ఈ కొత్తగా ప్రాజెక్ట్ క్రియేట్ చేశాము. ఫస్ట్ దాన్ని ఆ కోడ్ యాస్టిస్ కాపీ చేసుకున్నాం. కౌంటర్ వివాడో ఫైల్ కొత్త సోర్స్గా, డిజైన్ సోర్స్గా ఫస్ట్ దాన్ని కంపైల్ చేసి సిమ్యులేట్ చేసి అది ఎర్రర్ వచ్చింది. ఏదో xdir.sim అని ఒక ఎర్రర్ వచ్చింది. మళ్ళా కాసేపు ఆగి సిమ్యులేట్ చేసి ఇప్పుడు సిమ్యులేట్ అయింది.
ఓకే సార్.
సో వెదర్ వాట్ డస్ ఇట్ మీన్?
అది చూపిస్తానని చెప్పగలను సార్.
ప్రస్తుతానికి అయితే ఎర్రర్ లేదు. వీఆర్ కంటిన్యూయింగ్. ఎర్రర్ ఉంటే మళ్ళీ చెప్తాను.
ఓకే ఓకే, అదే హ్యాంగ్అప్ చేశాను.
ఓవర్ ద ఫోన్ మాట్లాడదాం. ఇది స్టూడెంట్ సిస్టంలో నెట్ ఏదో ప్రాబ్లం ఉంది, అందుకని.
ఓకే, మీరు ఇప్పుడైనా చూపిస్తుందా?
ఏం చూపించట్లేదు.
ఓకే, అయితే ఇప్పుడు నన్ను ఏం చేయమంటారు? మీరు ప్రొసీడ్ అవుతారా? అయితే
నేను ప్రొసీడ్ అవుతాను. ఏదైనా ఉంటే ఓవర్ ద ఫోన్ మాట్లాడదాం.
ఓవర్ ద ఫోన్. ఓకే ఓకే
ఓకే సార్. నెక్స్ట్ ఏం చేయాలి? ఇది పాత ఫైల్
పాతది సార్, అది కొత్తది.
రైట్. సో నెక్స్ట్ గో టు ద సోర్సెస్. ఈ సిమ్యులేషన్ క్లోజ్ చేద్దాం. సో ఫస్ట్ వివాడో ఫైల్ క్రియేట్ చేసాం. నెక్స్ట్
Hello, sir. Hello.
వచ్చిందా?
Please speak.
వచ్చిందా?
Hello, sir. Hello.
సౌండ్ ఇంకా
సార్ ఇంకా రాలేదు దాంట్లో వచ్చినట్టు ఎంతసేపు
వచ్చిందిరా.
హలో సార్. ఇప్పుడు నెట్వర్క్
హలో.
హలో సార్.
ఎస్ సార్. హలో.
స్క్రీన్ షేర్ ఉంది. హలో సార్.
సార్ ఎస్ ఎస్.
హలో సార్.
హలో సార్. యా టెల్ మీ. Am I not audible?
రావట్లేదు సార్.
హలో.
సార్ వాయిస్ కానీ నేను రావట్లేదు సార్.
జాయిన్ కాలేదు.
నేనైతే జాయిన్ అయ్యా, వాళ్ళ వాయిస్ వినిపిస్తుంది. Yeah, welcome back once again. So I hope the demonstration was very much clear to all the participants, and they were able to reproduce the same what I have illustrated through online. So moving
Sir,
further,
Srinu, sir,
sir, tell me, sir.
your voice is low.
Now is it fine, sir?
Yes, fine, sir.
Okay. Okay, so far we have seen the combinational circuit implementation and sequential circuit implementation, and also we have covered the use of intellectual property IP cores in our designs. So the IP cores which we have used is the inbuilt IP cores. Maybe tomorrow or a day after tomorrow, we will see how to design our own custom IP core from the Verilog HDL description. So the combination and sequential logic has been completed. I request all the participants to practice more designs. So in order to have a very good hands-on experience. And in this, at the end, we have left out with one important concept, that is a finite state machine design. So in this half an hour session, I will be dealing with only the theoretical aspects of the finite state machine. And tomorrow I will come up with one real-time example of a design using the FSM concept for developing a custom hardware architecture for one particular application. And then if time permits, then we will see how to design custom IP cores. And after that, we will solve some very good real-time examples. So this is how the flow going to be like. So before starting, I would like to share my screen. So I hope my screen is visible, right?
Yes, sir, it's visible.
Yeah. So I was talking about FSMs, right? So FSM stands for finite state machines. In this, we have two different types of FSMs. We have Mealy FSM and Moore FSM. So I request the participants, if they are to go through the theoretical aspects behind about all these Mealy and Moore machines. So there is one particular variant of an FSM that we call it as ASMD. ASMD stands for algorithmic state machine with data part. But in between, there is also one more variant that is called as FSMD. So FSM means purely controller logic. FSMD means controller plus data path. So both are separate. So controller part will be defined separately and data part is defined separately. Whereas ASMD, it is a more advanced version of FSMD, where we have integrated control and data part logic. So it is integrated control and data part logic. So in the industry standard, we will use ASMD for designing. Of course, we'll also use basic FSMs as well if it is a pure controller. However, if you have any algorithm or a process, so maybe we have, because if you take digital signal processing, that is DSP, or else some wireless communication, maybe having some protocols, so on and so forth, or any process or an algorithm. Say, for example, in communication technology, you might be heard of linear block codes or convolutional codes. So on and so forth, etc. So whenever you're designing a specialized hardware architecture for these kind of systems, maybe in DSP related or wireless communication related. So all, if what is the underlying concept, all these things usually have some particular kind of an algorithm or a procedure or procedural steps you need to perform in a particular sequence in order to get the end output. So for these kind of a systems which involve any algorithm or a procedure or a steps, so how do you map those kind of thing on FPGAs? That means how will be mapping them in the form of a physical circuit that is sitting on FPGAs. So in all these cases, we use the concept of ASMD. So that's why, as the name suggests, A stands for algorithmic state machine. So generally, any kind of a state machine, it resembles to be a controller circuit. So, however, if you take any of the DSP or wireless communication, along with the controlling, there is also data associated where you will do some data manipulation operations. So those all things comes under the data path logic. So that's why it is since the control and data both are integrated together in this variant, and we call it as ASMD, algorithmic state machine with data path. So we will look into its general structure. So the general structure goes as follows. So this I'm taking it from one of my patent document. So for your understanding, I'm just showing you the figure. So as the name suggests, algorithmic state machine with data part. So the dotted boundary, whatever you're seeing here, is the ASMD. And within the ASMD, you have a integrated control and data part logic. So both are integrated together, but when it comes to interpretation in the form of a diagram, so what we do is, so if we take this as entire ASMT, so in that, we tell like there are two different blocks available as shown in this figure. So the first one is the control part logic, and second one is the data part logic. Yeah, so maybe this you can call it as data path logic, and this you can call it as control path logic. So if you take either the data path or the control path, we have three sub logic elements. So first one is called sequential state register logic. Sorry. sequential state register logic, and second one is called combinational next state logic, and third one is the output logic. So in both the cases, you have three different logic elements. As the name suggests, sequential state register logic, these are purely registers as shown in this diagram. So it has a clock input, it has a data input, and it has data output. So just like a D flip-flop. And the sequential state register logic, we are talking this as a clock. It has data input and data output. This data output is fed back to the combinational next state logic. And here there is some kind of an operation that we do in the combinational next state logic. And that combinational next state logic provides the necessary data to the sequential state register logic. This we have already seen in our counter-based design. And the sequential state register logic also drives the output to the output logic. And from this output logic may directly either pass this as an output, or else it may do some manipulation and it may pass the output. So since these are control.
Sir, your voice is reduced.
Okay. So since these are the control lines, now is it clear, right?
Yes, sir.
Since these are the control lines, these control lines will go up over here. So this is what I'm saying. So we have sequential state register logic. Let me highlight it over here. So we have a sequential state register logic. Since why we are calling it as a sequential, because we are using a clock signal. And why you are calling it as a register logic? Why? Because this is a register with a D input and D output. So it takes in the input from the combinational next state logic, and the output is fed back to the combinational next state logic. And this combinational next state logic may take inputs, additional inputs, maybe external inputs that you can see here, command inputs. It can take external inputs, or it can also take some internal status signals, so on and so forth. And also for each register, there will be a feedback output. So that also it will be taking, and depending on certain conditions. So what are those conditions? Those conditions we will define for this block, which is marked in blue color. Conditions we will be defining. And depending on that, it will update its sequential state register logic. Once the register logic is updated, what it will do? It will give that to the output logic as well as the combinational next state logic. It depends. It's not mandatory like it should drive both. It depends. So from the output logic, either it may drive the internal circuits as shown in here in this figure, or else it may drive the outputs of the module. Similarly, this is the control logic, control path logic. Like that, we also have data path logic. So in this data path logic, again, the scenario is same. We have combinational next state logic. We have sequential state register logic with a clock, with a data in, data out. It is driven by the combinational next state logic, and this output goes to the output logic. From there, again, it may reroute to the routing logic and combinational next state logic. And then the output logic may also drive the external outputs. So this is how it looks like. A typical FSM, ASMD architecture. And coming to the, since I told like it is a state machine, the state machine may have state diagram as follows. Say for example, this one. So it may be a finite state machine. So in this is just an illustration. So this is having S0 state, S1 state, S2 state, and S3 state. Each state has its own significance. So whenever we are giving a power, it switches to the ideal state. So any FSM, same concept, or any ASMD, same concept, it switches to the ideal state. From the ideal state, what it will do, depending on the conditions, it will do state transitions. And whenever a transition occurs, it enters into another state, depending on a condition. And it will try to perform the operations which are defined in that particular state. And once the operations are done, depending upon the condition, it may either remain in the same state or else it may jump into the previous state or the another new state. So like that, whatever the functionality that you are defining across different states, it will go, the machine will traverse through different states and perform the operations in each and every state, and finally it returns to the initial state. It is the whenever you are designing an any FSM or an ASMD, you need to keep in mind like from wherever you are starting and how many states you switch. Ultimately, after completing all the tasks, you need to return back to the uh, original initial state. So the initial state is called as the ideal state in any state machine. So we need to have a complete path. So state entry and state exit, that conditions you need to define very clearly. And you need to check like there is no path should be abruptly terminated, and all the paths, whatever the direction or whatever the switching it takes, it ultimately from each and every state, it ultimately returns back to the initial state. So that you have to check. Ultimately the machine should come to the ideal state, so you have to define in that particular manner. So, how to design an ASMD? Generally, you'll be having a you end user will give you some specifications. So, depending upon the specifications, what you will do is you will be deciding like how to design your machine, and that entire process may be divided into sub processes, maybe A, B, C, and D. So in each state, what are there may be processes like independent processes or dependent processes. So what are the independent processes that you will try to segregate and divide? And in each process, you may be doing it in one particular state. So when a description is given, what you have to do, you have to draw an ASMD chart. So what is an ASMD chart? The chart says like what are the operations that you need to carry out in each and every state. That is called as an ASMD chart. So for illustration, I'm just showing an example. A typical ASMD charts looks like this. Uh, so the first box, whatever this box, this is called as a state box. In the state box, followed by the state box, you have a decision box. And followed by the decision box, you will have conditional output box. So whatever the outputs that you are defining in the conditional output box, those outputs are called as melee outputs. And if at all, if you are defining any outputs in the state box, those outputs are called as Moore outputs. So this is called an ASMD. So whatever this dotted line that you are seeing, this is the ASMD chart of the S0 state. In S0 state, see how it is entering when the power is up. When you switch on the machine, it directly jumps into the S0 state. After jumping into the S0 state, here it is checking one condition. If that condition is false, then what it is doing? It is returning back and again waiting in the S0 state. So this waiting continues until a particular condition is satisfied. So the ASMD in remain ideally remains in the S0 state. This is the condition. So when one particular condition is met, then what it is doing? Then it is performing some task in that state, and after performing the task, it is switching to the next state that is defined as S1. So what it is going to do in the S1 state? So that we have another ASMD chart in the S1 state, which is showing the operations that are performed in the S1 state. So again, it has an entry point. Again, it has a state box. So how all these things I have drawn means with respect to an algorithm. So I told we are discussing about ASMD, right? So algorithmic state machine with data part. So you'll be having a set of algorithm. So that algorithm I mapped into that algorithm is there. From that algorithm, I have decided to map it on the hardware using 4 finite states. And in 4 finite states, what I did in each state, I have defined some set of operations that I want to do. So what are those set of operations that I have represented in the form of this chart? So this chart is called ASMD chart. So in S1 state, after entering, again, there is a decision box. Depending on decision, it will take different path. And there is again conditional output box. So again, decision box, conditional output box. So depending on these decisions, so whatever it may be, what it will do, it will either go to S0 state if it takes this path, or else if it is taking this path, it re-enters into the same state. That means it remains in the same state. Or else if it is taking something, any path like this, then what it will do, it will either like this or from here to here or like this, it will go to S2 state. So this is, don't get confused. Whatever the data in between this chart that is irrelevant for you. I'm just explaining for the sake of your understanding. Tomorrow we will take one small example. In that example, we will see how to draw this ASMD chart. So like that, we have to define ASMD charts for each and every state. Once this chart has been prepared, from this chart, we can directly map it into Verilog HDL. There is a standard template available. Verilog HDL template that I will discuss with you tomorrow. A standard HDL template is available exclusively for ASMD. So once you define your ASMD, once you finalize your total number of states, and after that, once you finalize what are the ASMD charts of each and every state with these decisions and conditional outputs, so on and so forth, the state switching, etc. Then you can transform these charts into Verilog HDL by using a standard template. Then once your description is complete, then you can do simulation. You can verify the functionality. Once the functionality is met, the process is same. You do synthesis, implementation, run bitstream, and put it on FPGA. Your circuit will work. So for high-end designs or very complicated designs, we will generally follow ASMD procedure only for those processes which have a resemblance with respect to an algorithm or a process. So for all those things, we will be try to implement it in ASMT. So this is a brief introduction about ASMT. And in tomorrow's session, we will take one real-time example. I will show you what is a ASMD template, and with the template, we will take one example problem. From that, I will try to draw an ASMD chart. From that ASMD chart, we will write a ASMD specific HDL template for that problem, and then try to realize a circuit out of it. So with this, I will conclude my today's talk, and we shall meet tomorrow, and we will follow it up with subsequent experiments.
Sir, thank you, sir. Srinu, sir. We'll meet you
Okay, sir.
tomorrow by 10 o'clock.
Okay, sir. Thank you very much.